Hey guys. So the problem we have today reviews the concept of the law of universal gravitation. So without further ado, let's get started. So we have a problem here that asks us to calculate the force of Earth's gravity that acts on a spacecraft that's located 2 Earth radii above Earth's surface if its mass is 1,850 kilograms. So one thing that I really like to do before any physics problem is I like to draw a diagram of what that physics problem entails. Here we have the Earth and the spacecraft, the two objects of interest. I also drew out that the distance between their surfaces is 2 Earth radii apart. I also drew out that the mass of the spacecraft is 1,850 kilograms. Now, with all this information, they're asking us to calculate the force of Earth's gravity acting on the spacecraft. So, whenever they ask us to find the gravitational force between two objects, we have to turn towards Newton's law of universal gravitation. What Newton's law of universal gravitation basically says is that the gravitational force between these two objects is equal to the gravitational constant, which is 6.67 times 10 to the power of negative 11 newtons times meter squared over kilograms times second squared. So the gravitational constant times the mass of the first object. In this case, we can consider the Earth to be the first object, so I'll just say the mass of the Earth, times the mass of the second object, or the mass of the spacecraft, that I will denote SP, all over the radius squared. So a lot of times where the problem comes when it comes to these type of problems is a lot of people don't understand what the R means. The R is the distance between the two objects' center. That means the distance between center to center of the two objects. This is shown by the green line. So we have to square this quantity. So not only do we need these two Earth radiuses, the surface to surface distance, but we also need the radius of the Earth and the radius of the spacecraft. Now, because they don't give us the radius of the spacecraft, we can assume that the radius is so small that it's in fact negligible when it comes to calculating the gravitational force between these two objects. But what we do need to know is we need to know the radius of the Earth. Usually, a lot of times, they provide you with the radius of the Earth. It's usually on a formula sheet, or it could be located in the problem. But for the case of this problem, I'll just write out the radius of the Earth, which is 6 million, if it lets me draw it out, 380,000 meters. That is the radius of the Earth. So we have the radius of the Earth, and we have 2 Earth radii apart. So really, if you want to think about it, the R is equal to 3 Earth radii. All right, 3 Earth radii. Because we don't really need the radius of the spacecraft, the R is equal to the 2 Earth radii plus the additional extra Earth radii that we need to calculate R. So if we were to plug and chug all of the values we do have, we know that the gravitational constant is 6.67 times 10 to the power of negative 11. I will not write out the units, excuse me for that, but just, for the sake of space, I will not draw out the units. The mass of the Earth. Now, once again, usually they'll provide you with that information, but for this case, since I don't have it written out anywhere, I will give you that information. And the mass of the Earth is 5.98 times 10 to the power of 24 kilograms. So this mass times the mass of the spacecraft. Well, they give us the mass of the spacecraft. It's 1,850 kilograms. This whole quantity divided by our radius squared. Our radius squared is really 3 Earth radii. That's really what R is equal to, squared. So I guess we could also say 9 Earth radii if we, square this 3. And once again, to clarify, the R value, this R value comes from the center to surface of the Earth. the distance they are apart from surface to surface, and because the radius of the spacecraft is so small, we don't really need the radius because it's negligible in the grand scheme of calculating the gravitational force. So our r will be equal to this 2r value, these 2 Earth radii, plus another Earth radii. So 3 Earth radii in total. And because we're squaring that value, it'll be 9 Earth radii apart. So it'll be 9 times 6,380,000. So when we plug all this into our calculator, we should get the value of 2014.3 newtons. And this should be the answer to the problem. Thank you for watching the video, and I hope you tune in to another one.